Good afternoon. My name is Wang, and I'm from Intel. In this presentation, I'm going to introduce using hardware accelerators to accelerate non-migration of virtual machines. Those guys here are also from Intel, and they are contributors to this project. Let's have a look at the agenda of this presentation. So in total, I have 5 parts. In the first part, I'm going to introduce the goals of this project. And in the second part, I will give a high-level give an introduction of the high-level architecture of this solution. And in the third part, I will introduce some important features that are used in this solution. And in the fourth part, I will show some test results. And in the last part, I will introduce some future works that we plan to do. Okay, let's start from the project goals. So today there are some pain points in non-migration. So the first one is that virtual machines with memory-intensive, write-intensive workloads are difficult to migrate. So this is because the guest writes to the memory, they dirty more pages than the pages that can be transferred during migration. So the second one is VMs with large memory size usually takes long time to migrate. The third one is the VM migration may consume large network bandwidth. So there are some existing solutions in the current queue. For example, people may choose to use the CPUs to do compression, like a multi-threaded compression with ZDeep. And the problem is that it's slow based on our experiments. And the second issue is it consumes too many CPUs from the host. So this is not expected from the cloud vendors. So our solution is to offload the compression part to Intel QAT, quick assistance technology with efficient approaches. So by efficient, I mean higher migration throughput. So this is measured by how many pages we can transfer the from source to destination during migration. So the higher, the better. And the second one is lower CPU utilization. So we don't want to waste more CPUs from the host. So the second goal we have here is to have a common design ready for future more accelerators to join. So on the upcoming Intel Software Rapid CPUs, we will have data streaming accelerator, short for DSA, and Intel Analytics accelerator, short for IAX. So we have these two more accelerators to be integrated into the CPU chip. And we want to take advantage of them to process the guest memory during migration as well. And also we wanted to have a smarter selection technique, which smartly and dynamically select an appropriate accelerator to accelerate non-migration. So I will introduce this a little bit more in later slides. So let's have a look at the architecture of this solution. So on the source machine, so on the bottom here, you can see that we could have multiple accelerators here, and each of them have their own software stack, like the QAT library and the driver. And on the top, there are two threads here. So the migration thread is the one that's already in existing queue. So in the migration thread, I conclude it into 4 steps. The first step is the migration setup. So basically, it will do some preparation for migration, including the accelerator device initialization and the device pooling thread creation. So in the second step, the migration thread will do the page searching. So it searches for dirty pages to process and send it to the destination. So in the third step, we will do a smarter selection. So the migration thread will select an appropriate accelerator based on the history of the acceleration efficiency. So once it decides that, for example, using QAT is more efficient, so it will choose QAT to process memory for the following pages. And the fourth step is to dispatch requests. So once an accelerator is selected, it will compose a request data structure and submit it to the device to do processing. For example, if it's using QAT, and there may have multiple QAT compression engines, so it may dispatch the requests to those compression engines in round-robin fashion. And for the device polling thread, its main job is to poll for responses from the device. So the response here means that the previously submitted request has been processed. And once a response is obtained by the polling thread, it will release the request data structure. And it blocks when there is no response ready. So the second thing the polling thread doing here is to send the compressed data along with the related header to the destination through the network. So in this model, we basically have a split of the migration flow. So in the current migration flow, the migration thread is responsible for searching for dirty pages and then send it to the network. So in this model, the data transfer is given to the polling thread to send. So here is the picture on the destination side. It's similar to the one that we saw on the south side. So on the bottom here, it also have those accelerators, and on the top it has the two threads as before. And the migration setup is similar as the south side, so it will do some initialization work. So the difference here is it has a page receiving step. So this step is it receives the data from the network, and then the migration thread parses the migration protocol. For example, we added a multi-page protocol, so there is a multi-page header, and also it will select an accelerator to process the memory. So the data, the header, like the header tells the migration thread on the destination side that which accelerator to use. For example, if the source side uses the QAT to do compression, then on the destination side, it will select the QAT to do decompression. So for the device polling thread, on the destination side, its job is simple. So it adjusts the polls for responses. So once a response is obtained, then it will release the request data structure. It also blocks when there is no response ready. And for the device, the decompressed data are DMA'd to the QEMU memory directly. Okay, let's go to the third part. So I will introduce some features that I used in this solution. So the first feature we used is zero copy. So it allows, with this feature, it allows the accelerator device to directly access to the guest memory. So the second one we use is the multi-page processing. So the current migration flow only supports single page processing, meaning that it finds only one dirty page and then compress this page and then send it to the migration, to the network. So with this feature, the migration flow is able to process multiple pages each time. And the third feature is acceleration request of caching. So this feature just caches the acceleration request data structure for efficient memory allocation. So I will introduce more details about those three features. So for zero copy, so at the migration setup step, the migration thread needs to pre-allocate and pin. The QEMU memory needs to be pre-allocated and pinned. So this is to prevent the memory to be swapped out during migration. So on the destination side, the memory will be unpinned when the migration is done. but this is not needed in the future when we have VFIO based driver. So I will introduce in our future work. So for the request composing, on the source side, the DMA, we will set up a DMA buffer for the source device to process the memory. So the DMA read buffer, it points to the QEMU memory. So like the QAT device can directly do DMA read from the QEMU memory and then compress the guessed data. And for the DMA write buffer, it's allocated by the library, for example, the QAT library. So when the compression is ready, is done, the data are DMA write to the buffer. And on the destination side, the DMA read buffer is allocated by the library. So there is a piece of buffer. And the DMA write buffer points to the QEMU memory. So the device reads the compressed data from this library buffer and then do decompression. So once decompression is done, the device do DMA write to the QEMU memory directly. So this achieves the zero copy. So for the multi-page processing, so here is an example that we have 12 pages. So the migration thread will find multiple dirty pages one time. For example, here it finds that page 01 is dirty, and it composes a data structure that the dirty page starts from 0 and size 2, meaning that there are 2 pages, consecutive pages. And the second group of dirty pages starts from page 3, and it has the 4 pages. And the third group starts from page 8 and page 9, and it has 3 dirty pages. And then the migration thread do the request composition, and it composes the request which is submittable to the device. And it also needs to set up the DMA buffer. So it's a scale together buffer. So like here, it has 9 buffers. So the DMA buffer points to these 9 pages, and it's chained together. And the orange box here is the buffer allocated by the QAT library. So the QAT device fetches data from the QEMU memory and then do compression. So once the compression is done, the data, those 9 pages, the compression of these 9 pages, the result is written into the orange box, which is allocated by the QAT library. And then the device polling thread will transport those compressed data as a whole to the destination side. And for the data, each one is associated with a multi-page header, which tells the address of the QEMU page. Like on the destination side, when the data is received here, so it knows that there is multi-page header, and the payload is the compressed data, and then the migration thread on the destination side will compose the request, and it finds for the DMA buffer, the destination side address is calculated by the multi-page header, which tells where is the QEMU page that should hold those decompressed data. So the device reads data from the compressed data and do decompression, and then writes those data to the destination side, the QEMU memory. So for acceleration request caching, this is a common technique. So during the device setup stage, the migration thread pre-allocates some amount of acceleration requests data structure and fills them into the cache pool. And during the request composing stage, the migration thread will allocate the request. So instead of doing the malloc, it directly take a request from the cache pool. Once the requests are used up from the cache pool, it will do malloc. So And then it initializes the request based on the new pages to send. So for the response pooling thread, when a response is obtained, the thread frees the request to the cache pool. So instead of doing the calling the free syscall. Okay, let's have a look at the test results. So for the tests, we tested on the Intel Xeon CPU E5 2699 before running at 2.2 GHz, and this is the Broadwell CPU. And for QAT, we use the PCIe Gen 3 QAT card. So it's a PCIe card plugged into the PCIe slot. But on server-rapid CPUs, we will have QAT integrated into CPU, and it uses PCIe Gen 4. So the speed will be much faster on the upcoming Intel server-rapid CPU. So for the DRAM, we use the DDR4 and running at 2666 megahertz. And for the network card, we used a 40 gig network card. So for the migration setup, the downtime we use is 300 microseconds. So it's the default downtime used in QEMU. For the network bandwidth, we didn't set at a limit, so it can use up to 40 gigahertz, but in reality, it won't consume those much bandwidth. For the compress level, we set it to 1, so this is the fastest speed to compress. For the multi-page, we added a new parameter called multi-page, so meaning that the migration thread can process multiple pages each time. So we set the value to 63. This is the maximum value can be supported currently. So for the guest, we have 3 types of guest to test. The first type of guest has the 4 vCPUs and 32 gig RAM, and it runs a workload with writing compression-friendly data. And the second type of guest has 4 vCPUs and it has 32 gig RAM. But it runs a workload which writes sequence numbers to memory. So sequence number is not very compression friendly, but it's still okay to compress, not difficult also. So for the third type of guests, it has 8 vCPUs and 128 gig RAM, and it runs a Memcached workload with the reading and writing random numbers. So random numbers are relatively difficult to compress. We will see the compression ratio later. So let's have a look at the first test. So we run this dirty workload inside the guest, which writes data to the guest memory in a specified dirty read. Like here, we can set it to write 1,000 megabytes per second. And for the data, so there is something probably you need to understand first. So for the throughput, it's the migration throughput, and it's measured by how many pages we are transferred from the source to destination. So the higher, the better. And to make the numbers simple, so I put the multiplier here. So for the non-compression case, it can send like 17 multiply 10,000 pages per second to 29. Multiply this number. So for the 16 CPU case, so it's a little bit, it's almost 2 times larger, more than 2 times larger. For the QAT, so it's around 5 times larger. So we can see the normalized throughput here. So the QAT case has much larger migration throughput than the long compression case. So for the largest migratable dirty read, it means that we tune this number, this dirty read inside the guest, and we get that if we tune the number to like 1,200, then this VM cannot be migrated without compression. So this 1,100 dirty read inside the guest is the largest dirty read that the guest can have to ensure it can be migrated. So for the 16 CPU case, it supports this number, and for the QAT case, it's much larger than the low compression case. And for the extra CPU utilization, it means how many CPUs are used in addition to the migration thread. So for the long compression case, there is no extra thread, so it doesn't consume extra CPU. So for the 16 CPU case, it consumes 678 CPU percentage CPU. It doesn't consume all the 16 CPUs because this data pattern is easy to compress. So for the QAT case, it's less than 40%, so it's much less than the CPU compression case. So for the compression ratio, you can see that the QAT compression has a higher ratio than the CPU ZDIP compression. So the compression algorithm we use here is the same. But the compression ratio is different. This is because the multi-page compression. So when we have multiple pages, because for this workload, it writes all ones to the memory. So this repeated one can generate only, for example, one or single one as the compression payload. So in this case, multiple page can have the higher compression ratio. If we don't have these repeated numbers, the compression ratio between the QAT and the CPU compression will be similar. We can see from the next slide. Here for this sequence number, so it's not repeated, it's just a number from 0, 1, 2, 3. So we run this workload inside of the guest, and for the migration throughput, we can see that the QAT case is still much larger than the log compression case. So interesting here is that we find with 16 CPU compression, the migration throughput is even lower than the low compression case. This is because the compression isn't efficient with CPU compression. So it actually de-accelerated the migration. So for the largest migratable data rate, so for the QAT case, it's still larger than the low compression case. And for the CPU utilization, the CPU compression case consumes all the 16 CPU. And for the QAT compression case, it's less than 70%. So the compression ratio between the CPU and the QAT is similar here because they use the same compression algorithm. So for the third test, we use we set up the Memcached environment using this. So basically, it's a client, a Memcached client called Memstep client, and it writes random numbers to this Memcached memory pages. So the random number is much more difficult to compress than the previous data pattern. We can see from the compression ratio here, it's only 1.6. But the QAT compression case still has an advantage over those two cases. So it's like more than 2 times faster for the migration throughput. And the migration time here, infinite means that the VM cannot be migrated. Like in the low compression case, or the CPU compression case, the VM cannot be migrated. But with QAT case, it takes around 60 seconds to successfully migrate the VM. Okay, let's have a look at some future works that we plan to do. So the first one is VFIO Driver-based zero copy. So the current zero copy is implemented based on the UIO-based QAT driver. So this requires the QEMU to be root privileged to get the virtual address to physical address mapping via the page map. This may be difficult for some cloud vendors because their QEMU doesn't have root privilege. And this also requires QEMU to pin its memory. With VFIO-based driver, we will have the VFIO support to do this. So for the QAT's VFIO-based user space driver is still work in progress, and we will be able to switch to that later. And the second work we plan to do is smart acceleration support. So this comes with the idea that DSA can do a delta of the dirty memory. So the functionality is the same as the XBZRE in the current QEMU. So it finds out the exact pages that the exact bytes that the guest dirties. For example, if the guest only writes 1 byte, so there is no need to send the entire 4KB page to the destination. DSA can help to find out the 1 byte. So this works efficiently when the guest only modifies a small part of page. But we know if the guest writes the entire 4K pages, the 4K bytes each time, then DSA delta encoding might not be efficient. So in that case, we can use QAT to compression the 4K bytes instead of doing the delta processing. So we wanted to have a smart acceleration here. So with this technical, the migration thread will be able to dynamically switch to use QAT. IX is also an accelerator that can be used to compression. So it can select either QAT or IX to do compression, or use DSA device to do a delta processing during non-migration. So this will rely on a prediction based on the compression ratio history and the delta encoding history. So, for example, we can choose to compress the 10 requests at the beginning and find out what's the compression ratio, and also using DSA to find out the encoding rate. If the encoding rate is higher, then for the upcoming pages, we can choose DSA. If the compression rate is higher, we can use QAT for the following processing. So that's all for this presentation.